Hey there, it's Shannon Math Myers, and today we're going over an example from 6.2. So let's check it out. First of all, let's look at y equal to the summation as n goes from 0 to infinity of c sub n times x to the n. Now, we're going to need to find y prime. So we need a y prime. So y prime will equal to the summation as n goes from 1 to infinity of n times c sub n times x to the n minus 1. And then finding y double prime in terms of the summation, we will have the summation as n goes from 2 to infinity of n times n minus 1 times c sub n times x to the n minus 1, which is n minus 2. Good so far? Awesome. So now we just plug these things in to our summation and then get the indices of the summation to be the same, or the limits on the summation to be the same. So we have y double prime minus y prime equal to 0. We'll kind of block this part off. So substituting in y double prime, we'll have the summation as n goes from 2 to infinity of n times n minus 1 times c sub n times x to the n minus 2 minus y prime. Y prime is the summation as n goes from 1 to infinity of n times c sub n times x to the n minus 1. And this is all equal to 0. Cool, cool? All right, perfect. Now, we want to get the summations to be the same. So we basically are going to let k equal to n minus 2 for the first one. And so writing this in terms of n, isolating n, we would have n is equal to k plus 2. And then on this other one, we would have k equal to n minus 1, which in turn would give us n equal to k plus 1. So rewriting these summations, we will have the summation when n is equal to 2, then k is equal to 0. So this will start now from 0 and go to infinity. And then we will have n, which in this summation is k plus 2. I'm going to write everything in terms of k. And then times n minus 1. So again, k plus 2 minus 1 times c sub k plus 2 times x raised to the k minus 2. So k, n in terms of k, remember, is k plus 2, and then we'll have minus 2. So that's that first summation. The second summation, which is subtracted, will be minus the summation Now this time the k's will be a little bit different. So when n is equal to 1, the start of that summation, k again will go to 0 and then go to infinity. And then n is k plus 1. We have times c sub n, so we'll put our k plus 1, times x to the n, k plus 1, and then minus 1. And all of this is equal to 0. So now let's see how it all shakes out. So we will have the summation as k goes from 0 to infinity of k plus 2 times k plus 1 times c sub k plus 2 times x to the k. That's the first summation simplified, minus the summation, and it's written in terms of k, as k goes from 0 to infinity of k plus 1 times c sub k plus 1 times x raised to the k, and all of that is equal to 0. Factoring out our common factor of x to the k, we will have the summation as k goes from 0 to infinity, k plus 2 times k plus 1 times c sub k plus 2 minus k plus 1, that quantity, times c sub k plus 1, and that's all times x to the k, and it's equal to 0. So we basically will be setting the quantity that's inside the summation equal to 0. So we'll have k plus 2 times k plus 1 times c sub k plus 2 minus k plus 1 times c sub k plus 1 equal to 0. And if we isolate c sub k plus 2, let's see what we get. So we would add that second term to the other side. So that'll give us k plus 2 times k plus 1 times c sub k plus 2 is equal to positive k plus 1 times c sub k plus 1. And then isolating c sub k plus 2, do you see the k plus 1s will divide out, and we'll have c sub k plus 1 divided by k plus 2 is what c sub k plus 2 is equal to. Cool so far? So now, this of course is going to be for k equal to 0, 1, 2, ... So now, plugging in the first few terms, right? So let's find out when k is 0. So for k equal to 0, we'd have c sub 0 plus 2 is equal to c sub 0 plus 1 over 0 plus 2. That's going to give us c2 is equal to c1 over 2. And continuing, c sub 1 plus 2 would equal to c sub 1 plus 1 over, this is for k equal to 1. Now for k equal to 1, this is what we would have. We would have c sub 1 plus 2 is equal to c sub 1 plus 1 over 1 plus 2. That will give us c3 is equal to c2 over 3, which is equal to c1 over 2, plugging in for c2, over 3, which is c1 over 2 times 3. Now, coming back to c2, just in case, do you see that we could write this as c1 over 1 times 2? This last one we did could be 1 times 2 times 3. So maybe the formula is going to be c1 over 2 factorial. And this one is definitely right now c1 over 3 factorial. So let's see what happens when k is equal to 2. We'll get c sub 2 plus 2 is equal to c sub 2 plus 1 over 2 plus 2. We would get c4 is equal to c3 over 4. But that in turn is going to be c1 over 3 factorial over 4, which, sure enough, is c1 over 4 factorial. And so it will continue. So, therefore, the solution of the differential equation is going to be y at x equals. Well, you're going to have your y1 at x plus y2 at x. So y at x will be equal to, our y1 at x will be c0, and then y2 at x is what we just found over here. So y2 at x is going to be c1 times x plus 1 over 2 factorial times x squared plus 1 over 3 factorial x cubed plus 1 over 4 factorial x to the 4th plus dot dot dot. Right here, this is almost e to the x. Right? But what's missing is the x to the 0 over 0 factorial equal to 1. That's our missing term. So if we rewrite y at x equal to c0 plus c1 times, so remember, if you're going to adjust something, we need that 1, right? So if we just put -1 plus 1, that's going to balance out the expression here. And then we would have plus x plus 1 over 2 factorial x squared plus 1 over 3 factorial x cubed plus 1 over 4 factorial x to the 4th plus dot, dot, dot. So, okay, that's going to give us y at x is equal to c sub 0 minus c1 plus c1 e to the x, where y1 at x is equal to c0 and y2 at x is equal to negative c1 plus c1 e to the x. Cool, cool? All right, so there you have it. I hope this helps, and I hope you have a wonderful morning, afternoon, or evening whenever you're watching this show. And hey, if you like what I'm doing, go ahead and click the subscribe button and like the video. Bye.